Okay, so we'll start off. So we finished chapter 4, and now we'll move on to chapter 5. So just a real quick covered previously. So we covered the laws of thermodynamics. Okay, so that's a no-brainer because this is a thermal class. But so we covered the laws of thermodynamics. Chapter 2, we covered energy flow problems. With the corresponding process efficiency. Okay, so for example, we started with the first law in energy balance form. We got energy in minus energy out equals the change in energy of our system. Okay, and we can go from a kind of a block diagram way of looking at it, and I can put it in rate form, energy in dot, or I could do it in non-rate form, but let's do it in rate form, so I'll put a dot above these, and energy out in rate form, and inside I got a delta U dot. And of course, I could get rid of the dots. The dots represent the time derivative. But energy balance rate form, first law, variation of first law, rate form, draw a schematic. Of course, I have my boundary. And I got all the forms of energy coming in, all the forms of energy coming out, coming in, all the forms crossing the boundary. I got everything within my boundary is the internal energy. Electronic, thermal, magnetic, whatever it might be, all the forms of energy within my boundary is my internal energy. And so then if I want to write out an efficiency expression, I have energy out, useful, over energy in, equals 1 minus Q loss over energy in. Okay, and of course, if I want, I can put dots above it to represent in rate form or non-rate form. It doesn't matter. It's just a time derivative of the whole thing. They cancel out. You still have an efficiency. So this energy in, this one, and that one is all forms of energy in. Likewise, my energy out, that's all forms of useful energy out. Yes?
So the energy out that's not useful is reflected in the change in energy of the system.
So we could say that this is 1 minus the energy out not useful, right? Or the rate of energy out not useful. Typically, the energy out that isn't useful is in the form of heat or the heat loss, because that's typically what it is. But there could be other forms of energy, but typically there would be the heat loss, that's not the unuseful heat, that's rejected. There could be some other terms up here, but for a simplistic way of looking at it, we just say it's the energy loss over all forms, or the heat loss over all forms of energy in. But friction, you slide a block on a I just take my pencil or my pen, I go across the table, I go across here, I generate friction, right? And then you hear sound, but coupled with that sound is heat loss. And I can't get it back and put it back into my pen or put it back into me. No, there might be some of that heat loss that I can put back into me, and that's why we have all these different technologies related to thermoelectrics, Peltier devices, and different things like that. There's a lot of huge billions of dollars being put into minimizing the amount of heat loss. So just as an example of this, if I have a power plant, okay, so here's my power plant with a big smokestack. Coal burning power plant, whatever it might be. They're using some of that coal to produce electric energy, but some of the heat is leaving here, right? So what do they want? What is like a very general thing to do? Let's put a thermoelectric as big as this room around the smokestack, and let's suck out the heat from this and turn that into, right, electrical energy. So there's a lot of focus on using some of this lost heat, but still, even when you do that, the thermoelectric device is only so efficient, so it can only convert so much heat into electric energy. So then we would get, if we drew another blocks around here of a thermoelectric, right? And so I have some Q loss that goes into the thermoelectric. But if I draw a boundary around this thing is only so efficient, and then it comes right back to here. But now I drew my boundary around my thermoelectric, whereas I could do a boundary around my whole power plant, right? So my energy in is all the coal I put in, and all the energy it took for me to put it in the furnace or whatever it might be. And then it converts it, there's efficiency of the conversion process, but then if I do a box around this whole thing, there's going to be some heat loss. And so all my energy in is all the mass forms, and we could just simplify it. It's the rate at which we can put coal into the furnace, right? That's all my forms of energy in. Here's my delta U. So in rate form, if I'm constantly putting in coal at a given rate, this is 0, right? Because it's producing, the coal plant's producing energy at steady state. But then I have some energy out. Part of the rate of energy out is the power out, right? Electric power out. And the other part of the energy rate of power out is the heat loss. And then related to this, so I would have some line coming out of here, which says electric power. And then I would have heat. And we can't get back, we can't take this heat back, put it back in, because then we have some loop system, and then it goes back, and we can't do that. So another way we can do is we can build another system. So people are talking about things like that. But anyways, this is the simplified way of looking at it, because usually heat loss is the unuseful energy from some type of process. So that's what we kind of touched on in chapter 2. Of course, there was some, chapter 2 was an introduction to the first law of thermodynamics, and then at the end we talked about what is most practical, and that's the efficiency of a process, and then I just used these expressions. And then if you go back, and there's a bunch of different equations that describe efficiencies of processes, but they all are derived straight from this to this, and then you can write an expression for the form of energy in, say it's shaft work in, right? This might be electric power, this might be electric power out. So there's a bunch of different other forms of this, but they're all derived from these basic equations. Okay, and then we moved on to chapter 3. And then chapter 3 was devoted to saturated or liquid vapor mixtures. And in general, we could have a saturated, pure substances, saturated forms, right? And regards to saturated forms, I have my bell curve, and I have the saturated liquid line, saturated vapor line. In between is my liquid vapor mixture, right? And here I have my super heated vapor, and I have my sub cooled liquid. And we can write expressions for the specific volume of a liquid vapor mixture in terms of its quality factor, and that's just x Vg plus 1 minus x Vf, where this is the specific volume of a pure fluid. And then I can do the same type of thing for the internal energy. So I have x Ug plus 1 minus x Uf. And then we moved on to chapter 4, which dealt with energy analysis on closed systems. So, closed system, no mass flow. In, out, E across boundary. And coupled with this, energy analysis on closed systems, no, it was mainly devoted to boundary work. And then we can write it work on. We got minus P dV for boundary work by P dV. So boundary work, just change in volume, expansion, contraction of the boundary, change in volume at a given pressure, that gives me boundary work. So now what we're going to deal with, energy and mass analysis of open systems. So I'll just underline here with closed systems. Now we're doing open systems. Of course, now that we have an open system, we have mass flow. So open systems are more practical. That's a pump. That's a power plant. Right? That's a real engine. So in chapter 4, we talked about a combustion engine where we only had looked at one cycle because we couldn't add any more mass after it combusted. Right? Now we're looking at more practical things, real systems, related to air conditioners, power plants, pumps, right? Turbines, jet engines, however we want to look at it. So we have to take into account both, well, really it's energy analysis on open systems and energy also in the form of mass. So basically heat, work, and mass. And kind of redundant to that, heat, mass, and energy flow. So let's just draw some kind of cartoon of my system and surroundings. So I drew a block, and then I have some delta E system, right? I have my boundary, and I can have in general energy out and energy in, and then I could break down that energy out into different components, and here I could have some mass in and mass out. Or I could say some work in or work out. Or I could say some heat in and heat out. And of course I could put this in rate form by taking the time derivative of everything coming in and out, or just put dots above all the symbols. So mass, like energy, is conserved. Cannot be destroyed. And then just kind of Einstein thing, E equals mc squared. So mass can be converted to another form of energy, right? But in general, it's not destroyed. These, standard, right? Physical laws. So conservation of mass, just like we had an energy balance related to the first law, we have a mass conservation balance. So mass conservation just basically says mass in minus mass out equals the change in mass in my system. So I have a change in internal energy in my system. Coupled with that, I have a change in mass in my system. And the change in mass in my system is non-zero if there's a misbalance between the mass in and mass out. And of course, I can write this in rate form. Mass in dot minus mass out dot equals delta mass system dot. So if I'm adding mass at a constant rate, 1 kilogram per minute, and I'm removing mass at the same rate, 1 kilogram per minute, then what can this be? 0. So that represents a steady state mass transport. Steady mass input, steady mass output. In that case, the time rate of change of my mass in my system has to be 0. Likewise, I could replace all these with ease. If I'm adding energy, 1 kilojoule, right, at a given rate, 1 kilojoule per minute, that could be in the form of heat, work, and mass. I'm adding energy at a given rate, 1 kilojoule per minute, and I'm removing energy at the same rate, 1 kilojoule per minute. Then my delta E, I don't have, but my time rate of change of my energy of my system has to be 0. That represents a broader sense of steady state operation. We could look at it a more specific case of just steady state mass, right, transfer to my system. Rate of mass in equals the rate of mass out. Or on a very more general level, steady state operation, which covers mass, all the forms of energy coming in. In that case, I could have only mass leaving, no mass coming in, but I have heat coming in. Okay. So let's just kind of a review of that. So related to this, the boundary of the system defines the control volume. I want to underline that. So, we're going to talk a lot about control volumes the rest of the lecture. So, related to this, boundary of the system. If I define my system as a cube of ice coming in, okay, that is my boundary, my control volume for that cube of ice. Now, this has a control volume too. Now, I could say a control volume where it's just a packet of heat. Say 1 centimeter cube packet of heat. Now, typically we don't really think of heat in a control volume. It's more convenient to think of mass in a control volume, but nevertheless. Now, work is a different issue, a control volume for work, but a change in the control volume is directly related to boundary work. Just like if I expand this and extract that. So I have a control volume here defined by the boundary, but also my inputs have control volumes. So we're going to touch on that a little bit more. But the boundary defines, so whether it's the boundary of my system or the boundary of a packet of mass coming in, or a packet of all the forms of energy coming in. So I could have define a control volume of electrons coming in, right? Nevertheless. Okay. So rho equals m over v. Okay, that's just density. So from this, I can rewrite the mass of my system equals an integral over my control volume, rho dv. Okay. So move v over here, put it in integral form, take the integral. This represents mass of the system, total mass within the control volume. So it's just the integral form of the total mass of my system based off its density. And I could say constant density within my control volume. It's a constant, moves outside the integral, and basically all I have is my volume, and it comes right back to that, right? But density within my control volume could be it could have a distribution, and then I would have to take that into account. Okay. But mass of system related to that, just an integral form of this expression, right? Now I can take the derivative of this, d mass system dt, and then all I have is d dt, the integral over my control volume, rho dv. So if my mass was constant, I could take it outside the integral, and then I have to look at, well, if it's constant, you know that there's no d dt there, right? So then it would just end up being, do I have a time rate and change in my control volume? If so, then I have a time rate of change in the mass of the system. Now, of course, this could be a function of time, and this could be a function of time, right? And then I could rewrite my integrand a little bit differently, and I could put this as, a little bit different. But right now, I just want to point out, you can go from here to here, so we can go in rate form, and then I'm putting all this in the context of a control volume. So the rate of change of mass within my control volume, calculus form looks as such. So previously we had related the conservation of energy, energy in minus energy out, equals the change in energy in my system. And in rate form, energy in dot minus energy out dot equals the change in energy in my system dot. And of course, this is dt delta E system. It's the same thing. So the time rate of change of energy in is the rate of net energy transfer into the system / control volume. Now the control volume can change, right? Typically we try to keep it constant unless we want to know boundary work. Then we're more interested in the change in the control volume, or the time rate of change in the control volume. Right, related to an engine, the time rate of change in the control volume tells you the horsepower related to the horsepower out. So, E dot time rate of change of energy transfer into the system / control volume by heat, mass, and work. So same thing, out of the system / control volume by heat, mass, and work. And the time rate of change of this is the rate of change in internal kinetic potential, etc. So I should put internal with brackets, so it's quote unquote internal. And internal can be in the form of kinetic, potential, magnetic, electric, whatever it might be, thermal. It's the internal energy. So internal energy within a control volume of a specified system. So my specified system could be the inlet of a pump. It could be the pump in general. So rate of change in internal energy. So it's kind of the rate of change of internal energy within a control flow. what does steady state mean? I talked about this. So steady state implies, on a very general level, delta E system equals 0. So the time derivative of this equals 0. So steady state for mass flow, steady state mass flow, steady flow of mass, dt delta m control volume equals 0, which implies m dot in minus m dot out equals 0. Non-steady state, dt delta E system does not equal 0. Non-steady state mass flow, non-steady flow, dt delta m control volume does not equal 0, and then related to that, delta m dot minus delta out dot equals dt delta m control volume. So I'm just emphasizing this whole idea of steady state and the ramifications, whether we do conservation of mass, conservation of energy. So conservation of mass is just a subset of the first law of thermodynamics, right? All we're considering is mass as a form of energy in the context of the first law. So previously in chapter 2, we did look at energy of a flowing fluid. So if you recall, I had something. Energy associated with fluid flow. And then this part here, I wrote it out, and if we just looked at the mechanical part, we had 1/2 mv squared plus mgz plus pv. But then if we wanted to look at total, we had 1/2 mv squared plus mgz plus pv plus m times small u. So we already dealt with this. And so some of those problems you did in the homework on chapter 2 were basically the same thing you're doing in chapter 4, it's just we didn't talk about it as much. So in many ways, the problems in chapter 2 were more challenging than they will be in chapter 4 because you haven't had as much time to think about them. You were just thrown at an open system energy analysis, and you were asked to do efficiency back then. So previously chapter we dealt with this. So I just said this in words. Energy associated with a flowing fluid, right? I have my kinetic energy part plus my potential energy part plus my pressure volume kind of potential energy part. So I think of this as kind of like an internal energy, but this is a pressure-based one. And then I had my other internal part, so if I just look at the mechanical aspect, I have kinetic energy plus potential energy plus my PV. If I look at it total, I have my kinetic plus potential plus this other internal potential type thing. And then I have to add, so this one is related to temperature. So as I increase my temperature, I increase my internal energy, unless I have some really exotic substance. As I increase my temperature of my substance, the internal energy goes up. You have to have some really crazy stuff that usually only might even, I think I only have heard of a few things that happen near absolute zero, where you increase its temperature and its internal energy goes down, but then there's a lot of entropic things. But in general, increase the temperature of a material, its internal energy goes up. It's almost universal. And then this one is kind of an internal but pressure part. So as I increase the pressure within my control volume, what happens to its energy? It increases too. So you could just look at the ideal gas law to get the proportionalities. And so just writing this out, let's put in red here. Mechanical part. And the mechanical part has an internal part, but it doesn't have a thermal part that's internal. Now, of course, this thermal, this contribution to the energy of a flowing fluid, right, or a control volume of flowing fluid, has a pressure part in it too. Okay, I'm probably just confusing things. So let's just think of it in terms of temperature. So 1/2 mv squared plus mgz plus mp specific volume plus m small u. So back in chapter 2, they just talked about the mechanical part of a flowing fluid, and then I added this part to all the equations. I told you guys to add this right away, because really it's all of this. And so now in chapter 4, they're adding it on, so with not much distinction between the mechanical. So let's look at this little diagram here. So there's a center of mass associated with it, and so this is a flowing fluid, and it could be flowing fluid in some pipe. Okay? And it's flowing, and I define a control volume. And it has a center of mass. And that center of mass has a reference to some, say, sea level. There's a mass in here. Right? I have a control volume. I can do an integral over this control volume, and I can calculate the total mass with it. Constant density, all I need to know is the volume. Say this is 1 centimeter cubed. And I know the density. I can just multiply the density times 1 centimeter cubed. I get the total mass with it. Or I can do integral over it, right? So I have this. So that the mass, gravity, z, center of mass. So I have a potential part. Well, then this thing can be traveling at a velocity, right? My control volume. No, my control volume has a mass. So it has a mass. Traveling at a velocity, that gives me the kinetic energy part. And within this control volume, I have a pressure. And this is 1 over density. Right? So it has a mass with a given pressure. So as I increase the pressure within, I increase this other potential part. If I decrease the density, it goes up. But anyways, decrease it. Typically, these are coupled to each other, right? I'm just putting the mass up here. And then I have my other part. So this thing has a temperature, right? I drew a boundary, right? I had defined a control volume. So in order for me to describe the state of this, I need to know 2 independent intensive things. So once I define the temperature, and I say it's, say, water, I can go look up what this is. I know its mass based on the size of the control volume. And I got its total energy of this thing. Now this control volume could be changing, right? But in general, the control, when we think of fluid flow, the actual control volume does it. The best way to do it is the actual control volume, say 1 centimeter cubed, doesn't change. The shape changes. So when I'm here, I have elongated one. Now you can, in different contexts, look at constant volume, right? Or changing volume, and then you could look at the work associated with pressurizing it or something like that. That's kind of what a pump does. But I'm just highlighting this whole thing. I have a flowing fluid. I define a control volume. It has a center of mass. It has a velocity, right? There's a velocity of the center of mass. There is a temperature of this. There is a pressure of this. It has a total mass. And I have all of those, and I can calculate it. It has a density, right? Which gives me 1 over specific volume. So this control volume has properties. I define the boundary. Then I can calculate the energy of this control volume. So, okay, so I did that. Now let's consider enthalpy. So H is equal to U plus PV. So here I have a U, and here I have a U. Here I have a PV. So let's write it in small h form. H is equal to U plus PV. So I can take this and write it in terms of the enthalpy. So now I got M U plus PV plus 1/2 M V squared plus MGZ. So I got M H plus 1/2 M squared plus MGZ. I'll just put brackets around this. So you can kind of see with this flowing fluid and a control volume analogy that if I just think of it as pure laziness and getting rid of the number of symbols in an expression because my hand gets sore when I have to write more, it's more convenient to write the energy of a flowing fluid with H. From just purely my hand gets sore from writing more things down when I'm solving an expression. But in practicality, reducing the number of variables means you have less tables to look up. So now I don't need to populate, right, my expression with this as a function of temperature and pressure, and this as a function of temperature and pressure. Now I just populate my expression with this as a function of temperature and pressure. So a lot of times flowing fluid problems, open systems, it's convenient to express it in terms of the enthalpy. And just from writing it out, you can see that. But then solving problems. So, okay, so the time rate of change of energy out, flowing fluid, it could be in or out. It's just the time derivative of all this. So I got MH plus 1/2 M V squared plus MGZ. And I take the time derivative of this. And of course, this is in or out. Doesn't matter. And I can use product rule differentiation, right? So if I do this on the first term, I got M dot times H plus H dot times M. And I can do the same all the way throughout. Now, typically we're dealing with things that are steady flow problems in thermodynamics. Now, in real life, you're going to deal with non-steady flows. As soon as you graduate and you start working for a company, you're going to deal with non-steady flows, right? Something went wrong with the pump, right? It's leaking. You have your out, your M dot out is not the same as your M dot in terms of the useful M dot out. So in real life you have problems. So, but for the sake of the course, we're going to simplify it and we're going to say steady flow type things. So M dot, we end up taking it out, and then we just have H V squared and all this other stuff. We end up taking this and we simplify it to M dot H plus 1/2 V squared plus GZ. Because we're now from the context of this control volume, so this is my control volume, this is my rate form. What is it implying? To go from here, from this to this for this control volume, what is it saying?
That your M dot in is your same as your M dot out.
No, not quite. Just think of it not from this, just this right there. What is it implying? So if I write out this whole thing, I would have, just for like the first term, I would have m dot h plus h dot m, right? That term is no longer here, so what does it say about h dot?
There's no change.
There's no change in enthalpy. So if I look at the time rate of change in enthalpy of my control volume, what does that say? Enthalpy is a state function.
So state 1 and state 2 are the same.
Okay, state 1 and state 2 are the same, but what is a state function, simple terms, temperature and pressure? What does that say about the temperature and pressure of my? They're not changing in time. This control volume is coming in at constant velocity, constant temperature, constant pressure. And in this formalism, it's saying something. If I draw a boundary, this is a form which describes the rate of mass coming in of constant temperature, constant pressure, constant velocity. Now, in a turbine or a pump working at steady state, that's exactly what happens. I have my inlet to my pump, and I have mass coming in at constant velocity, right? There's a mass flow rate in. The temperature of the inlet isn't changing. The pressure isn't changing. So this is just a way of kind of writing it into, it takes a while. You have to think about it some more. I mean, it's not intuitive. You have to think about the control volume. You have to think about this thing crossing a boundary, another boundary. This is my control volume, my fluid coming in. This is my boundary to my system. So m dot is the mass flow rate. Now, of course, as this increases, so does this. At constant pipe diameters. So this is coupled to that. And if you look back at some of the homework, there was this A times V is equal to m V dot, the volume flow rate. A V equals V dot. And I derived this based off density and derivatives of delta x and things like that. But anyways. So it seems like a diversion, but it's a very, what I'm talking about here with control volumes crossing something is something you need to think about in order for you to properly solve problems that are real, of unsteady, non-steady problems. You could just throw the equation and always write. So to solve problems in this class, in the book, you can take all the expressions related to a flowing fluid and you could just reduce them down to the m dot times h plus 1/2 v squared plus gz, right? You could just immediately go to that expression and solve 90% of the problems in the back of the book. But when you leave, it's not going to be like that. So I'm trying to emphasize that you think about the control volume crossing. So back to enthalpy. Using enthalpy, we have energy balance. Energy balance equation becomes say in rate form, En dot minus E out dot equals delta E control volume, or I could put system there, and then I got work in dot plus Q in dot plus energy in flowing fluid minus work out dot plus Q out dot plus energy out dot flowing fluid equals delta E control volume. Okay, and we simplified this one and we got rid of the PV and the U and we just created it to an H, right? So in this regard, I have delta E flow and fluid in equals d dt mh plus mv squared over 2 plus mgz, and the same d dt. I should put in mh plus mv squared over 2 plus mgz out. Energy in, flowing fluid dot, energy out, flowing fluid dot, work in dot, power in, work out dot, power out. Right? The time rate of change of work is power as units of watts, right? Joules per second is a watt. And likewise, I have the rate of heat input, a heat flux, or if it's small q, it's a heat flux. But anyway, so I have rate of heat input, heat, q dot, heat, rate of heat output. Without the dot, it's just the total heat input. Of course, this is a control volume, and I have some delta energy of my control volume. So all of this applies to this expression where I've written this out, and I've I've combined my internal energy within my per unit mass within my control volume and my pressure times specific volume, and just lumped it into an H. And of course, I can simplify this further and just do m dot h plus v squared over 2 plus gz. So I can simplify this, and when I do it like such, I'm saying that the temperature, pressure, and velocity, and my height, the output height, isn't changing in time. So then I can lump all of this times the mass flow rate in. Now if the temperature is changing, and so if I have an unsteady process, right, the temperature of my mass out might be changing in time. Then this is no longer a constant, and I need m dot h plus m times h dot in there. The velocity might still be the same or all that other stuff, but if I had some temperature dependent process, right, my reaction stopped working as well, or I had some extra heat generation, right? So just a side note, specific heats and the relationships to U and H. So the specific heat at constant volume is partial U, partial T at constant volume. Specific heat at constant CP is the specific heat at constant pressure. This is partial H with respect to temperature at constant pressure, specific heat at constant pressure. So this is small u. I can rearrange this one. Delta U equals CV at T dt. On a big U, I have a mass, right, times my CV at T dt. I can do the same thing here. I can take this. So I got delta H, my change in enthalpy, is related to CP, which could be a function of time, or temperature, dt, or big H. So typically we just say that the heat capacity isn't changing, and we just put in a constant value, but really it's a function of temperature. So the heat capacity at water at room temperature is 4.184, right, kilojoules per kilogram per Kelvin. If you go to 99.9 degrees C, it actually decreased. And then of course, if you go from you boil it into a vapor, the heat capacity goes from on the order of 3 point something to really, really small value. So heat capacities are functions of temperature. A lot of times you just assume it's an average one. So I can do delta U U2 minus U1 equals the integral of CV at T dt from state 1 to state 2, or from temperature 1 to temperature 2. Likewise, H2 minus H1 equals the integral from state 1 to state 2, or temperature 1 to temperature 2 at constant pressure. Looking at this, I can lump this into, I can simplify it. CP average, T2 minus T1. Or I could do the same thing, CP average, T2 minus T1.
For the U, would it be CV average?
Yeah, sorry. Thank you. And of course I can do big U's, my mass, CV average, temperature 2 minus temperature 1, big H, mass, CP average, temperature 2 minus temperature 1. So if I were to plot CV as a function of temperature, it does something like this for almost all materials. It plateaus at really high temperatures. And of course, then you might have a phase change. And so if water, well actually, water went the other way. But anyways, it plateaus at higher temperature, and then you might have a phase change. But I should have drawn it the other way. That's for gas, it looks like that. Water actually goes the other way. But so I have this. If I want to know if I have some process that works from T1 to T2, right? I have some process that changes the temperature of my input fluid from temperature 1 to temperature 2. I would just pick the average value between these two. It's pretty close to a straight line. And instead of putting in some function that describes the temperature dependence of the heat capacity, I just use an average one and get a pretty close answer. So that's what I recommend you do for all problems, is pick an average value of a lot of things. Just go straight to this form or that form. If this is small, once you do that and this is small, right, it ends up being a small quantity, what good does it do to do the whole integral and include the temperature dependence if this is small to begin with, right? So if I want to know if the change in internal energy of my fluid doesn't change much due to temperature, really it's more of a magnetic type thing, then why add all that extra work when really this is a small number relative to some other form of energy? So I always recommend, simplest thing, just make average values for a lot of properties, do a calculation, then evaluate how important it would be to do more detailed calculations. About 80% of the time you don't need to do more detailed calculations because you just did this and you found out that all you can do is increase the efficiency by 3%, right? From this, so what do you care if you have a accurate prediction of the efficiency to 10% or 5% when you only can increase it by 5%? It doesn't make any sense, right? So, long story short, when you're doing calculations, pick average values. And then you can do analysis on whether you need to do any more. So, okay, so let's go back to this fluid flow and pipe. And now I've kind of have a different, so I have some velocity distribution. And I can define an average velocity. So we have friction, so I have fluid flow in a pipe, and there's friction at the walls, so this represents what is called as a no-slip boundary condition, right? So the velocity at the wall is 0, and then it's maximum in the center. So there's a velocity distribution of my fluid flowing through a pipe. And I can calculate the average velocity, and that's what basically this red dashed line is. Right? If I were to do the first moment or the average value of the velocity, it would end up being somewhere like here. And if I just approximate it as a triangle, I take 0 plus this, right? And then it'll give me right in the middle. Of course, it's going to be a little bit more weighted towards this way because it's not a triangle versus the middle. But anyway, so I can do this. V average is the average velocity or average speed through a cross section. Average speed through a cross section. So I haven't drawn it, but remember how I talked about a cross-sectional area? So if I have pi of a given diameter, right, it has a radius. So pi r squared gives me that surface area. So average speed through a cross-section, so just imagine this being a pipe, right? And so I'd have average speed through a cross-section. So we're going to get to that. So this is in words, so 1 over AC, where that's the cross-sectional area, times the integral of E. So now I'm doing, this is, so if you remember from calculus, you have to do first moments, or the, the mean value, or the center of mass. So this is, the average velocity in this case is over the cross-sectional area.
What's that subscript? That V?
This is normal to the cross. V sub n, the n represents normal to the cross-section. So my pipe's like this. It has a normal, right? Cross-sectional normal. So I could have a bunch of things that are going all over the place, which in a gas, right? If it was a gas flowing in really slow, there would be random motion of the gas molecules. So if I picked over some cross-section, so at one point they'd be going down, some might actually be going backwards, but the net average velocity would be something. At the walls it would still be 0, but I would have this messy distribution. Even in liquid there's some random fluctuations. So this just cares about the normal to the cross-section. So if I have my pipe, here's my surface area, there's a normal. All I care about is that velocity dot product with the normal. So in words, Vn, velocity distribution, normal n to the cross-sectional area. So on a note, Vn equals V dot n. Here's a picture where this represents, this part right here represents Vn. This is n. And then this is the actual velocity. And this here represents dA. So I can write this, get rid of the dot product if you remember, just pretty general. Vn equals V dot n, which equals the magnitude of V times cosine theta. Right, and here I have some theta. So this is just a typical way of doing it. Some funky looking cross-sectional area. But I've put it in a differential cross-sectional area. So this could be a pixel on that. So if I pixelate my inlet to my pipe, I pixelate it, and I make a little square here and a little square, and I just make it a bunch of pixels. This would be 1 pixel. Of course, I have an AC across the total cross-sectional area. This is just an element of it. So I did all this with the mass flow rate to introduce a lot of concepts, but I'm going to go back to the mass flow rate. So the mass flow rate follows a similar way of expressing it. So let me move it down. So you can see here's my average velocity, and now I have my mass flow rate, which is an average value, right, in this context. So there I had 1 over AC. I forget my 1 over AC now. So, okay, so this is my mass flow rate. If I want to do an average, then I have to do the 1 over A in there. But anyways. So for a uniform or constant density across my cross-sectional area, I have m dot as such, which means that I have rho AC 1 over AC times an integral over my cross section Vn dAc. I'm going to put red brackets around this one. This part here is my average velocity. So then if I just look at this, my m dot equals rho AC times an average velocity. And if we look at this, right, this is related to what we had earlier, so I can rewrite this a little bit differently, but this is related. So an area times a velocity gives me a volume flow rate. So m dot equals rho v dot. So this is what we've been using. So I just did all this stuff to point out that we can do all this calculus and all this other stuff, and you can prove that we're just looking at average values of the velocity of the mass coming into our system at constant density. But I can rewrite this one, right? Well, I have that before, but anyways, rho v dot equals m dot, or the integral over AC delta v dot equals the integral over AC Vn dC. So v dot AC 1 over AC integral over AC Vn dC. Again, I'll put red brackets here, and this is my V average. So I just basically, I said this in words, and then I went through the whole calculus version, showing that V dot equals V average times a cross-sectional area. And we had, in some of the homework problems and some of the example problems, and in the example problems for exam 1, this expression is used a lot, where the volume flow rate is constant, so the average velocity out times the cross-sectional area out equals the average velocity in times the cross-sectional area in. If the volume flow rate in and out of my system is constant, so just an application, V dot equals constant, that implies that V average out times AC out equals V average in AC. So this could be V1 times A1 equals V2 times A2. A lot of glossy eyes. Good.
Say that for just a second.
Most problems, the volume flow rate is constant, right? A pump doesn't increase the volume flow rate, it increases the pressure so you have flow, right? But the volume flow rate, it doesn't increase the volume flow rate. The volume flow rate is the volume flow rate. If the volume flow rate changes, you have a leak in a pump. A turbine at a dam doesn't increase or decrease the amount of the volume flow rate of the river. It is what it is. If it were to do that, there would be a lot of evaporation going on in it, and it would be going up into the atmosphere, right? So usually you're dealing with problems where it's a constant volume flow rate, and then if you look at pipe type, or so a dam takes a big cross-sectional area and then shoves it down to a smaller one, but the volume flow rate is the volume flow rate, given that the water levels are constant, right, at a dam. So let's just finish this up for this. So differential mass flow rate. So I have my differential delta M rho Vn dA equals rho V cosine theta dA. Yeah, sorry. Rho V dot net mass flow rate, the net mass flow rate. Wanted to do this. So I have my differential mass flow rate. Here's my system. Okay. And I can have mass leaving it. Okay? So I have a control volume, but given that I've defined a control volume, I have a control surface. So the boundary has an area. Within the boundary gives me a volume. So my net mass flow rate is related to an integral over the control surface. Sometimes I wonder why I throw all this stuff out there in lectures, because we don't use it that much, right? But a good reason why I'm doing it, and I keep on throwing things in integral notation, is to get you to remember that there's a reason why you took calculus, right? And it's because everything is related to areas, volumes, rate of changes in volumes, slopes. And sometimes we just simplify things to average values. But if you don't know why you're lumping it into an average value, you don't know how to minimize a problem to simplified forms. So before you can really do that, you need to be able to think of things in rates and volumes, so you know why you're making it just an average value, because you're just saying it doesn't matter much. The density in here isn't changing, or whatever it might be. So I'm trying to throw at you that you want to think of things in terms of integrals and derivatives. Even though most equations and most of your books have gotten rid of all that, you need to think of it in integrals and differentials. So this kind of complicated thing, and I'm just getting to the net mass flow rate, right? I wrote all this stuff out, but and then I'm going to write a simpler version for the the conservation of mass. M dot in minus M dot out equals d dt delta M control volume, and so I rewrite this d dt delta M control volume plus M dot out minus M dot in equals 0. And this part here is my d dt of rho over cv rho dv. And this part here is my integral over my control surface rho v dot n dA. So if you remember Gauss's law, doing calculations on charges and stuff like this, this is just it's just mathematically the same type of principle, but now we're not talking about electric fields and things like this based on the amount of charge within. Now we're looking at flow out of a system or into a system. So general conservation of mass follows this same type of principle where I have d dt rho cv rho dv plus the integral over my control surface equals 0. So what is this? If I integrate over my my density of my control volume, what is that? This is all the mass inside my control volume, right? Control volume has a density. We could say it's uniform density. Do this over so the time rate of change in mass within my system is equal to the flux of mass in or out. Now, if V has the opposites, so this is my surface normal. If V is negative, right? And for this to be balanced, so I could bring this over to the other side, but it is equal to 0. So this is just a long-winded version or a more calculus-based version of looking at the conservation of mass. Time rate of change of mass within is related to the flux of mass in or out. So this whole part here was m dot out minus m dot in. Okay, so let's just finish this up. I said that earlier, but I'm really going to finish it up now. So d dt. All I want to do is I want to take this into a summation type notation. Delta M control volume plus bracket the sum out rho Vn A minus the sum in rho Vn A equals 0. D dt delta M cv plus the sum out m dot sum in m dot equals 0. So related to this, if I pixelate my surface and I give each one of those elemental areas an area and I pixelate it, I have a average velocity normal to that, and I can just take this whole integral and break it down to some notations. So I take my sphere and I pixelate it, and then each one has the same area. This is what you write out when you're doing things, analytically. When you solve real flow problems, this is what you do with a computer. You take the integral and you write it in some notation, and then basically I could have one half of my sphere, say 1,000 pixels, right? All the things coming in, and then the other half is where they're all leaving. I could have maybe nothing coming in or out on the top, whatever it is, but I'm just pointing out. The time rate of change of the change of mass in my control volume is related to all the forms of mass coming in, right? The rates of mass coming in plus, I have to bring it over here, all the forms coming in minus, or the difference between them in and out. So, just one question. For steady flow, what is this reduced to?
0.
Well, it's already, so for steady flow, this is 0. So I have the sum of out m dot equals the sum of in. This isn't changing in time. So I did a lot of this stuff mainly just to get you guys thinking about calculus again.